Yeah, go figure. So, let's see. 7.5 continued. Partial fraction decompositions continued. And the last example that I did was the partial fraction decomposition for this rational function right here. Now, I'm not going to go do it all over again. Let me just remind you of what the decomposition looked like. It had a term over the x plus 2. It had a term over x plus 3. It had a term over x plus 3 squared. Okay, so we are taking care of various contingencies now. This was the example that I did for when you had repeated factors, right? Like the x plus 3 is repeated because it's got a power 2 there. Okay, so the next sort of contingency that we need to worry about is, what if some of the factors are those irreducible ones that I was talking about? So recall the irreducible factors. The prototypical example is x squared plus 1. You can factor this using complex numbers, but you cannot factor it if we were just sticking to real numbers. So these are kind of like their own little pain in the butt things to have to deal with. And here's how we deal with them. So let's just do an example. And this example is going to foretell what we're going to be doing later on, probably today, but certainly in the next section we cover. And that is how to integrate 1 over 1 plus x squared. So let's just give the simplest possible example involving an irreducible. So I told you can't factor this, so we can't really do a partial fraction decomposition. So we have to use another trick. It's one that I haven't shown you guys yet. So you pretty much should not know how to do this yet. Maybe someone knows. What's the trick? A trig substitution. So for now, just sort of take this without justification why I'm doing this. So later on, I'll show you how you would know to do what I'm about to do. For now, just watch me do it. And what I'm going to do is I'm going to make the substitution x is equal to tan of theta. So then dx is equal to secant squared theta d theta. And then this thing becomes the integral over 1 plus tan theta squared. And then on top, okay, it's secant squared theta d theta, which is a secant squared theta d theta on top. 1 plus tan squared. There's a trig identity. What's 1 plus tan squared? Secant squared. So we just get secant squared over secant squared. Cancel the secant squared. It's just the integral of d theta, which is theta plus a constant. And theta, let's see, we can invert this expression to get that theta is tan inverse of x. So this is tan inverse of x plus c. Okay. So just sort of keep that in mind. This is a calculation that it's good to have memorized, I suppose, just to know what this integral is. And this is a very typical example. So like I'll just mention, this would be probably a good model-like test question, for example. Like you should definitely be able to reproduce this, and probably something like it will be on a test. So, okay. Knowing that is one of the things we're going to use to handle the irreducible terms. And before I do an example, let me write down the rule. Okay, so term. So let's just give a general irreducible term, ax squared plus bx plus c. And it's that each one contributes a term of the form. So we'll have this irreducible part in the bottom. And on the top, here's the thing that's new, is you need to include an x. So you'll have to add a term like this to your partial fraction decomposition. And again, what's different about it is it has two constants, actually. One with an x term in front of it. And more generally, like if we had irreducibles with multiplicity, which would be an obnoxious pain in the ass to have to deal with. Like, we're not going to do any problems, but I'll just tell you what would happen if we had multiplicity. So that would be something like this, but to a power higher than 1, let's say to the m. Then we would get the following contribution to the partial fraction decomposition. So we'll have a1x plus b1 over it to the first power. We'll have, let's say, a2x plus b2 over this to the second power. And maybe you can see the pattern now. We'll have m of these. But if you ever had a problem with this, like, it's such a pain to have to do. There's so much like algebra and busy work and arithmetic. I don't think we're ever going to have to deal with this probability. But let's just to make sure we get it, let me just show you a couple of examples. You guys know, everyone copied this down? Who needs it? So, for example, 1 over x plus 1, x squared plus 1 has a partial fraction decomposition. 1 for this factor, as usual. And then for this irreducible factor, we'll need a bx plus c. Okay, so what I just said is exactly what I was telling you right here. Or how about an example with multiplicity? So 1 over x plus 1, x squared plus 1 squared would have a partial fraction decomposition of, all right, as usual, 1 over this guy, and then let's say bx plus c over x squared plus 1. And I need one more term for x squared plus 1 squared. And this will have like dx plus e. So, man, yeah, I'm not going to do an actual example with that. It would just be too much work. Okay, so there's actually only one thing left for me to tell you about partial fractions. I've already mentioned it, and that's what to do for when they're not proper. And if you remember, I said just do polynomial long division. Finally. So you first do polynomial long division, and then you do a partial fraction decomposition on the remainder. Okay, so I'll do one example for this. I'll do one example that will incorporate this scenario as well as this scenario. And then we can finally be done with all this partial fraction busy work business stuff. My example is this one. It's to integrate this guy. So is it proper? Nope. So first do long division. That degree is 3, by the way. Okay, so one of the reasons I wanted to do this example is just to remind you guys how to do polynomial long division, because maybe some of you guys haven't done it in a long time. And so this is kind of to refresh your memory on that. So this thing is x to the third plus 2 over, if I multiply this out, I get an x cubed plus x squared plus x plus 1. So the way long division works is we're going to write x, okay, let me give myself room here. X cubed plus x squared plus x plus 1. And then put the numerator under the box, which is x to the third plus 2. I could say like, some people like to say plus 0x squared plus 0x, if you want. Okay, what times this equals this? 1. So put a 1 here, then multiply that 1 back times this whole expression to get x cubed plus x squared plus x plus 1. Then I add, or subtract, I'm going to say subtract, or add the negative, either one. Okay, so subtracting this from this, the first term cancels out, and I'll get a minus x squared minus x plus 1. So this whole thing is equal to 1 plus minus x squared minus x plus 1. Cool. Okay, so that was an illustration of me doing what I was telling you guys to do right here, which is first do long division. Now, what we're left with, this one, is proper. So we can try to apply our other partial fraction decomposition tricks. Here, so let's just look at this expression right now. First step is try and write out what the form would be. So I should have an x plus 1 term, and I should have an x squared plus 1 term. And as usual with the linear term, it's just one number. For the irreducible, we'll have to write bx plus c, basically like I was saying right here. Okay, right, so this is equal to negative x squared minus x plus 1 over x plus 1 times x squared plus 1. And now let's take everything and multiply it by the denominator. So I clear all the denominators, and I get a with x squared plus 1, bx plus c with a x plus 1 equals this, negative x squared minus x plus 1. So now I just have to go through the arithmetic of finding these coefficients. Can we do any shortcuts, or do I need to equate powers of x? Like, I'm kind of lazy. Let's see if I can do a shortcut. Let me try to do a shortcut. Okay, what's one good choice of x? Let's do negative 1. I like that. Because if x is negative 1, then we'll get a times 2 plus, well, this term goes away. Gone. Equals negative 1 minus negative 1 plus 1. 2a equals 1. A equals 1/2. Any other good choices? I like negative 1. What's another good one? Yeah, we can do 0. It's not going to work out quite as nicely, but it'll give us something. So if I put in a 0 here, then I'll get a times 1. The b goes away, right? I just get c. All right, b times 0 plus c times 1 equals, well, minus 0 plus 1. Okay, so a plus c equals 1. A is 1/2. So I guess c is also 1/2. And can I plug in another value of x? It's kind of, I could actually plug in anything for x. Like I just need an equation. What do you think another easy number is? Yeah, I haven't done 1 yet. Let's just do 1. You got the idea. Okay, so yeah, a times 2 plus b plus c times 2 equals -1 minus 1 plus 1. 2, a is a half, plus 2 times c is a half equals -1. 1 plus 2b plus 1 equals -1. So 2b is -3, and b is -3/2. All right, so the integral of the original expression, x to the third plus 2 over x plus 1, x squared plus 1 dx, is the same as the integral of 1, a is a half, 1/2 over x plus 1, plus b is -3/2. And this is the same as the integral of 1 dx plus 1/2 the integral of 1 over x plus 1 dx minus 3/2 the integral of x over x squared plus 1 dx plus 1/2 the integral of 1 over x squared plus 1 dx. I deliberately wrote it like this as a sum of separate integrals because I wanted to bring home the point that each one of these is now something that we know how to do. We kind of have to use a different method for each one, but they're all doable, right? All doable via methods we have learned in this class. Like, okay, well, the first one, that's pretty easy. That's just x. Second one is pretty easy as well. That's a log term. The third one, what's the method for this? U substitution, good. So if u equals x squared plus 1, so du is 2x dx, then I'll get a minus 3/2, and I need to divide by 2 because of the 2, times 1/2. This thing would be the integral of, 1 over u. So that's ln of x squared plus 1. And on the last term, what's that one? Yeah, that's why I showed you that example of exactly this integral before and said that it's tan inverse. And we'll talk more about that later on. All right, so yeah, there's your answer. And that is all I'm going to do for partial fraction examples. These guys take freaking forever. Any questions? Okay, so that wraps up this section. Next, we're going on to 7.3. So I opened up the textbook and start looking at the material in section 7.3. And I'm lazily looking at the book, and I noticed the very last homework problem in section 7.2 is on the Wallace formula that I was having you guys watch a YouTube video on for extra credit. So I want to bring your attention to exercises 80 and 81 in section 7.2. On the Wallace formula for pi, right, which says that pi over 2 is equal to 2 over 1 times 2 over 3 plus 4 over 3 and 4 over 5 times 6 over 5 times 6 over 7 and so forth. Right, like I just did ask you guys to watch this video on this, and then I realized, hey, like your book has a problem on this. In fact, it's a couple problems. It's kind of in depth. It's pretty easy. Like I think it would probably be too hard for most of you guys, but I still thought it was interesting, and maybe you guys might want to take a look, and maybe I can even figure out some way to like incorporate it into the homework or get some extra credit for doing it or something. I don't know. I don't know what I'm going to do with it, but I think you guys should, if you're interested, which I hope you guys are, I think you should take a look. It gives a totally different way than the one that was seen in the video, by the way. It uses this trick of doing integrals of sine to the mth power of x dx on the interval 0 to pi over 2. Right, which we were just learning how to do in section 7.2. So by just evaluating this expression, you can derive this formula. It's pretty neat. Totally different than what was in the video. Okay, so what is 7.3 now? 7.3 is all about stuff related to that trick that I showed you to get this integral right here. That substitution that I made where I let x equal tangent theta. So I told you guys, well, how would you ever know to do that though? Right? So I'm going to show you guys how you would know how to do that. Via the method of trig substitution. So yeah, this is just one more trick that you can add to your handbag of tricks. I thought maybe I'd motivate this. How many of you guys like pizza? Right? It's like the best freaking food ever, right? I personally had pizza for lunch yesterday. I had pizza for dinner last night. And then I had leftover pizza for lunch again today. It was actually, last night was a tortilla pizza that I made. My own personal invention. You guys probably don't know nothing about that. But yeah, you can make a pizza on a tortilla. It's freaking delicious. You just gotta fry the tortilla enough so that it's not too like floppy or flimsy. So let's say that you had some pizza and you wanted to divide it up between you and your friends, but you can't cut it in the normal way. You can only cut it vertically for whatever reason. I don't know what your reason is that you can only cut it vertically, but let's say you can only cut your pizza vertically. So we've got a pizza, and let's say it's of radius r, and you want to slice it up, and you're going to take vertical slices like this and pass them out to your friends. Now, obviously, like this slice right here is going to be a bigger piece than this slice right here, right? It doesn't, just because they're of equal width doesn't mean they're equal area because of the shape of this circle. So it's actually not very simple to figure out a formula for what the area of this slice should be. Because, okay, like here, let's try to do it. So this is the equation x squared plus y squared equals r squared, or y is equal to plus or minus the square root of r squared minus x squared. The plus for the top, the minus for the bottom. Here, the minus for the bottom half, plus for the top half. So we can use our familiar formula to get that, say, here, if let's say this point right here is x, and we want this red area, and this is the origin, so this is 0, then the red area, that'll be the integral from 0 to x of the function on top is positive r squared minus x squared. The function on the bottom is negative r squared minus x squared. So that's just the same as twice the integral from 0 to x of root r squared minus x squared dx. And then, okay, so you and your friends, you're really hungry, right? You need this pizza, but you got to divide it up fairly. But you get to this integral, and you can't eat the pizza until you figure out how to divide it up fairly. And you think everything's all fine and good, but then you realize, wait, you don't know how to do this integral. Yeah, you can't do it with the methods that we've learned in this class up until this point. You can't. It's not possible. So what are you going to do? Yeah, you're going to do a trig substitution. And so trig substitutions all come down to exploiting those Pythagorean identities. Like when I did the example earlier in class today to get an expression for this integral, it critically hinged upon the fact that when I plugged in tangent right here, I had 1 plus tan squared, which by the identity we were able to replace with secant squared. Right? It all came down to that fact that we were able to make to transform that integral into something we could handle. So the trig substitution, basically, it all relies on this formula if you're doing it with tangent and secant, or there's basically only two of them. The other one is sine squared plus cosine squared. So pretty much every trig substitution will either be using sine and cosine or using secant and tangent. You might ask, hey, what happened to cosecant and cotangent? As it turns out, any problem that you can do with cosecant and cotangent, you can also do with secant and tangent. So I'll just keep things as simple as possible. Let's not make them more complicated than they need to be. And so yeah, basically you'll either use this formula or you'll use this one. Now, if we wanted to use this formula, here's the thing. So if I subtract sine from both sides, 1 minus sine squared is cosine squared. That's the key fact. Like compare to the polynomial 1 minus x squared. Looks kind of like 1 minus sine squared if x is sine theta. Okay. So, let's see. Let me finish doing this one now. Here's the substitution that I'm going to make. So, okay, here's what I want you to keep in mind. When you see an expression of the form 1 minus x squared as part of the integrand that you're having trouble integrating, I want you to make the substitution that x is equal to sine theta. And in the example that I was doing with the pizza, it's not quite like 1 minus x squared. It's r squared minus x squared. So there's a pretty easy way to take care of that. Let me first do another example. So how about the integral of 1 over 1 minus x squared dx? Let's just look at this one for a minute. And according to what I just told you, we should make the substitution that x is equal to sine theta. So then dx is cos theta d theta. And this thing becomes, okay, so on the top we get a cos theta d theta. On the bottom, it's a, 1 minus sine squared theta. Now do you see why I said that this whole method relies critically on this identity? What's the whole point? What can I now do? I can simplify this. So this is the whole thing with trig substitution. All comes down to the fact that this is the same thing as cos theta via this identity. So I get the integral of, cos theta over cos theta. So cosines cancel. That's just the integral of d theta, which is theta plus c, which is, what was theta? Theta was sine inverse of x. Cool. So there you go. Now, what I wanted to then point out is what to do when the number is not 1. So how about the integral dx over, how about 4 minus x squared? All I did was, like I've been telling you everything for when the number is 1 minus x squared. Now I made it a 4. Do you know what the substitution should be here? Because sine won't work. But this is, cos won't work either. We need to take care of that 4. But, so notice that 1 over 4 minus x squared is the same as 1 over, I'm going to factor out a 4. Yeah, that's true. Okay. So that's the same as the square root of 4 times the square root of 1 minus x squared over 4, which is the same as 1 over 2 times 1 minus, and 4 is 2 squared, so that's the same as x over 2 squared, which is the same as 1/2 times the square root of 1 minus x over 2 squared. So this suggests that we should let x over 2 equal sine theta, i.e. x equal 2 sine theta. And then this 1/2, it just goes in front of the integral, right? Like the 1/2 is no problem. So really, it's pretty much the same problem. You might, oh man, it's so great when someone drops that in the lecture hall. That kid must be so embarrassed right now. Got caught drinking whiskey in class, I guess. Okay, so yeah, except for these factors in front, it's almost like the same problem. You just got to make this minor adjustment. So I think that would allow me to have some pizza, right? Like now I can take care of this. What should the, so let's go because we're all hungry, let's go work on this problem. What should the substitution I make be? Because so you can kind of like take analogy with this one. I said x equals 2 sine theta was the correct substitution for this problem. I didn't finish the problem, but I kind of motivated that. So what should it be on this one? R sine theta. So if we make this choice of x, so then dx is r cos theta d theta. Okay, so the integral, the pizza slice area, which was 2 times 0 to x of root r squared minus x squared dx, is the same as 2 times 0 to x, the integral of r squared minus r sine theta squared, and then dx was r cos theta d theta. Oh, wait, let me change. These limits, I should not leave the limits in terms of x. I'll compute the limits at the end. How about? So inside the square root sign, I get an r squared minus r squared sine squared theta. And, okay, here, I'll just finish this. So this is the integral. If we factor out the r squared from both terms, I get a 1 minus sine squared theta. So I get a 2. Here, let's bring this r out in front. An r. Oh, and in fact, this r we can also bring in front, right? This guy, the squared and the square root cancel. So I actually get an r squared. Here, so this whole term is equal to r. 1 minus sine squared is cosine squared. So it's just r cos theta. Okay, this whole term here. So I get a cosine theta. I get another cosine theta, so that's actually cosine squared of theta d theta. Wait, is that what I was expecting to get? Okay, cool. All right, yeah. I did not work this problem out in advance. Sometimes I kind of like, improvising the lecture kind of on the fly. Like I kind of know where I'm going, but it's more fun if some of it's kind of made up on the spot too, So, all right. This is a 2r squared. Cos squared, we know how to integrate. That's 1 plus cos 2 theta over. Man, I feel like I made a mistake, though, because this is not the answer. Sorry?
Is it 2r?
What? Okay, all right, well, we'll see what this comes out to be. Or let's see, the 2's cancel. So this is r squared times, this integral is theta, and then integral of cosine theta is sine 2 theta over 2. Okay, I think this is fine. Okay, so, this is r squared. And what do we get? I got to put everything back in terms of x now. This is a definite integral, right? So here, this part's kind of interesting. Watch this part. Theta, according to my substitution, this right here gives that theta is the sine inverse of x over r. So that's what I should replace theta with here. And sine 2 theta is 2 sine theta cosine theta. Right? Isn't sine 2 theta is 2 sine theta cos theta? And the reason that I mention that is because, okay, so sine theta, that's x over r, according to our substitution, right? That's basically what I have written over there. Cosine theta is a little bit trickier. So let me write it right here. Cosine theta can be written in terms of sine theta. It's 1 minus sine squared theta. So that's 1 minus, 1 minus x over r squared. Yeah, so pay attention to this part. This is kind of a tricky aspect of doing these trig integrals, is how to put everything back in terms of x at the very end. So this, let me just write this out. So the 2's canceled, leave me with sine theta cos theta. So according to what I just wrote, the sine theta is x over r, and the cosine theta is this. So square root of 1 minus x over r. Okay, so what do I get? I get r squared sine inverse of x over r plus, if I multiply an r squared in here, one of the r's will cancel with this one, and one of them I'm going to move under the square root sign. So I'll actually get x times the square root of r squared minus x squared. I did that right? Yeah, like, go ahead. If I bring this r in here, right? Put an r squared here. One of them cancels with this one, and one of them goes inside and becomes a squared and cancels with that one. Okay? So this is the answer, right? I guess evaluated from 0 to, I just said x, but if you plug in 0, you get 0, so it's just the same as this. This is the answer. So you can eat pizza now, right? Like you got the air, just plug in whatever x. Like if this is 1 inch, plug in 1 inch for x, and you've got the area of your slice, man. Yeah, it's freaking pizza time. All right.